All right, so like I said, we're talking about expanding binomials, taking a binomial and raising it to different integer powers. When we do that, we're getting more and more complicated, like foiling or area method, however you want to do it, problems to expand it all the way. And you are probably wondering why. Why would we want to do this? Why do we want to know how to do this? When does this ever come up in the real world? What does it describe in the real world? Well, it tends to describe quite a lot of stuff, really. It describes things really well. For example, when there are two different outcomes and you want to know what's going to happen. So, for example, two different outcomes. Let's say a coin flip, heads or tails. And you want to know heads or tails. What am I going to get if I flip the coin? What am I going to get if I flip the coin twice? What am I going to get if I flip the coin 3 times? What am I going to get if I flip the coin 4 times? So in that sense, what you're going to be doing is you're going to be repeatedly multiplying some kind of probability. So if it's like a 50% chance that you get heads the first time, and then it's a 50% chance that you get heads another time, you multiply those two numbers, 50% and 50%, or 0.5 times 0.5, and you get 0.25. You see that there's a 25% shot that I'm going to get heads twice in a row. Now, let's look at that in an area model. So if I'm saying that there's a 50% chance, 0.5 is what H represents, a 50% chance of getting heads, tails is 0.5 as well, then there's kind of a variety of outcomes. So if we're going to do H, if we're going to do a heads or tails choice twice, what we're effectively doing is kind of multiplication. I'll show you why. So what we have to do is we have to pick either heads or tails, right? So that commits us to one of these two columns. So let's say we were trying to get heads twice. Well, heads once has these possible outcomes. If you get heads again, you have H squared. If you get tails, then you have HT. Now, the probability of either one of these is going to be the same. Really, all 4 of these boxes are going to be the same because heads and tails are equally likely. So 2 heads, H squared, is going to be 25%. A heads and a tail is going to be 25%, but also a tail and a head is going to be 25%. Those are effectively the same thing, right? 1 head, 1 tails. We're not going to distinguish between the order of them. So really, you'd get a 50% chance of where are we at over here? A 50% chance of getting tails heads or heads tails, whichever way you want to say it. You have a 25% chance of getting your tails twice in a row. So tails and then another tails is 25%. Okay, and if I wanted to keep figuring out higher and higher amounts of flipping going on, I would kind of extend this into a third dimension. Rather than having a flat picture, I could draw back into the background and make this like depth measurement also equal H plus T, which would give us another series, which would give us a series of, what would it give us? If we had H plus T, then we would get all of these multiplied by H and all of these multiplied by T. So we'd end up with like 4 in the front and 4 in the back boxes. So we'd end up with 8 different terms that we'd have to simplify down. But that would be multiplying the binomial H plus T times itself to the third power. Okay, so H plus T times H plus T to get a 2-dimensional area diagram. And then if you multiply by H plus T again, you get a 3-dimensional volume. Let me show you a picture of that so that makes a little more sense if it doesn't. So if we're doing A plus B, not heads and tails, but just A plus B, you get A squared, B squared, AB, AB. Okay, so you get A squared, 2 ABs, and B squared. If I take this now, this flat area, and let's say, I think they kind of lie it down flat, so you can see A, B here. It's like this A, this B. This tiny little cube in the bottom is this B squared multiplied by a height of B. Okay, so everything on the bottom layer is this area multiplied by a height of B. You can see B right here, that short length. So you get kind of these short boxes because you multiply by a short height. Okay, everything on top is these 4 boxes multiplied by A. So you get kind of taller boxes because A was a larger amount. But what do you get in total? You get 1A cubed, you get 1B cubed, and you get 3 different ways to make a square, so this large square in the front, multiplied by b, so it can be in that orientation. So I'm gonna read this out as like right to left, front to back, and down to up. So right to left is a, front to back is a, up is b. So that's a times b. This one is a times b times a, and the one on the back would be b times a times a. But that's just three different ways to get the same quantity, a squared b. For the same kind of idea, you have three different ways to make this one, a b squared. Okay, so we would expect similar outcomes if we were not doing a and b, but heads and tails. And we'd be able to calculate, if I want to get a cubed, or in that case of heads and tails, like h cubed, heads cubed, well, it's going to be a 50% chance times a 50% chance times a 50% chance. So that's like a 12.5% chance overall when you multiply 0.5 times 0.5 times 0.5. If this represented tails, it would be the same thing. A squared b would be 0.5 times 0.5 times 0.5, but there's three of them now. So instead of 12%, you'd have three times that much. This would be like 36% of outcomes would be two heads and a tail. And another 36% of the outcomes would be one head and two tails. So you'd have like 36% of the outcomes, 36% of the outcomes, 12%, 12%. Okay, let's look here at something that is not as even as 50-50. Let's talk about like a forecast, like if somebody's forecasting the weather on TV and they say, well, over the next 2 days, I expect a 50% chance of snow. Okay, what does that mean? Over the next 2 days, 50% chance of snow. Well, if we said there was a 70% chance of rain and a 30% chance of snow, and we wanted to take those odds 2 days in a row, what we'd be doing is we'd be doing r plus s times r plus s. Now notice that r and s total to 1, right? They're probabilities. We're saying that there's only two options in this example. We're saying there's only the option of rain or snow. So if you add these up, they need to total up to 1, the only overall option. Okay, the only overall thing is that we're either going to have rain or snow, so those two need to add up to a probability of 1, which means 100%. Okay, 100% of the options are covered by this. So if we have something that totals up to 1, r plus s, so 1 times 1, that means this whole area will also add up to 1. So whatever these four boxes are, add up to 100% of the outcomes. Okay, so one of the outcomes is it rains, 70% chance, and it rains the next day, another 70% chance. So that's 0.7 squared. We would get 0.49. We could get it snows at a 30% chance, times it snows again at another 30% chance to get 0.09. Or it might snow and then rain, or rain and then snow, which is the 70% chance followed by a 30% chance. Okay, so we get 0.21. Those two boxes are the same thing though, right? That's 2 days where half of them were raining, half of them were snowing. So we would add these two boxes together because they're like terms. Okay, and we'd say a mixture of rain and snow is pretty likely, 40%. All rain is the most likely because rain is the most likely, so at 49%. And all snow is very unlikely. It's about 1% chance that you're going to have snow 2 days in a row because it was a pretty low chance that you were going to get snow 1 day in a row. So to get it twice in a row would be an even more unlikely situation. Okay, you could do this with trinomials. We're not going to do this, but like if you thought like, okay, it's not going to either rain or snow, it might rain, it might snow, it might do neither. Okay, there might be three options. Well, if we had a trinomial, we could still make an area diagram. We could still solve for all of these combinations and say kind of what your forecast would be. But we're going to be just focusing on binomials for now. Okay, so that is kind of the general idea here. I also would like to show this in what I may be inaccurately calling a tree diagram, but it looks like a tree. It branches off, they branch off, they branch off. So I just want to describe what we're seeing in these pictures if you think of it as a series of choices. So if your first flip, you can get heads or tails, and your next flip, you can get heads or tails, and your next flip, you can get heads or tails. There's an option where you get heads 3 times in a row, but it's only one time. There's only one option like that. Okay, there's an option where you can go heads, heads, tails. So 2 heads and a tail. You can do a heads, a tails, and then your second head. You can do a tail and then 2 heads, a tail. Yeah, so that was 3 options where you had 2 heads in it. If you wanted 2 tails in it, 2 tails and 1 head, you'd also find 3 options. 1 here, 1, 2, leading back. 1, 2, and I'm probably missing one. 1. Say we want 2 tails. So 1 option there, 1 option there, and 1 option here if we start from the H and move our way backwards. Okay, so 3 options for that. And for t cubed, for tails, 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 well, only one way are we going to get that. We have to get tails every time. There's only one way to do that. Okay, so we multiply those probabilities. The probability of heads was 50%, so we do that 3 times. Over here, the probability was 0.5. We do 0.5 times 0.5 for the H squared. We do 0.5 for the tails, and there were 3 of those possible outcomes. Okay, so that's kind of a tree diagram model. Same thing for rain and snow. So if you can have rain or snow, and that branches off into a total of 1, 2, 3, 4, 5, 6, 7, 8 different outcomes. Well, one of the outcome was all rain. One of the outcome was all snow. 3 of the outcomes was 2 days of rain. 3 of the outcomes was 2 days of snow. If you plug in those probabilities that we set for R and S, then you're able to solve for the overall probability. So 3 days of rain, 34% chance. 2 days of rain, 44% chance. 1 day of rain, 18% chance. No days of rain, all snow, 2.7% chance. Okay, so this is kind of what these binomials are about. They're about situations where there's 2 options. So, rain or snow, heads or tails, win or loss. If you're working for the stock market goes up, stock market goes down. If you have some reason to have some kind of percentage to say, I'm 75% sure the stock market's going up. Well, what is your percent surety that it's going to go up 3 days in a row if it stays at that probability? That's one unique branch on many, many different options of how things could play out. But if you want to make the right trades and make a bunch of money, you need to understand what those options are and what their probabilities are overall. Okay, another kind of thing. So this ties into science. So I'm a former science teacher. I'm a science major in college, so I like to tie math to science as much as I can. And one thing that's good about this topic is binomial distributions, where you get, like 1, 3, 3, 1. You get a small number of rare events and a lot of common events and a small number of other rare events. So this is what all of our binomial distributions are going to look like as we expand them. If they had lots and lots of terms, you might see a bunch of terms that are kind of in the middle of that expansion, but you always just get one that's, to the a to the 5th power and b to the 5th power, and in the middle you'd have a squared, b cubed or something. So you always get this curve. You get a distribution of possible outcomes. And in science, we tend not to know everything so well that we can really predict exact outcomes. What we really know a lot of the times are we have like probabilities. We have kind of estimates for what we think is going to happen. We have a model. So for example, in a cancer treatment, let's say you have a new therapy for cancer and you think it has a 10% probability to cure a patient. So that's your assumption, a 10% chance of curing a patient. You have 500 patients who took the drug. So the expected number of recovering patients is 50, 10% of that. But in your trial, 75 patients responded. Okay, so what we're saying there is we expected it to be 50. That was kind of the middle. Okay, this graph is not showing this situation, but I'm just using it anyways. We're expecting it to be 50. We actually get 75. Now, if we got 75, we want to know, is 75 fairly likely to have come up? It's not the most likely. The most likely was 50. That was our guess. But 75 came up. Well, is that still likely? Or is 75 down here? Is 75 some extremely unlikely event? So if we can know ahead of time the likelihood of each outcome, we can assess our outcome. We can say, okay, this cancer treatment is doing something wildly different than we expected. It's way over here on this distribution. Or It's not doing what we thought it was going to do, but it's not doing so much different than what we thought. It's probably all right. Okay. That's really how science works. That's how being a doctor works, for example. Like, you are updating your assumptions. You have approximate ideas of what's going to happen for a treatment on any given person, but people are all different. There's all these different ways things could turn out, and you might have an idea of how likely you think something's going to work, and if it works a lot better than that or a lot worse than that, you want to know, does that still fit in your model or not? Or are you dealing with some weird outlier that really you shouldn't have expected to land on? So, for example, if we just read this graph as it is, if we talk about number of coin flips, you can expect that you're going to get 50 heads, 50 tails, but you might just get 100 heads. That's possible. It's like a 1 in 2 to the 100th power. It's like a 1 in many orders of magnitude, billions upon billions upon billions of one in that number chance. But it could happen. And if it did happen, you might be suspicious about the idea that there's a 50-50 chance when you're flipping a coin. Now, for a coin flip, it's pretty hard to make an argument that it's anything other than 50-50. So maybe you wouldn't revise your model after all. You would just say, wow, that was crazy lucky that I got that. But in a situation where your model was more based off other unsure things, like how a human body works or how medicine works in the body, you'd be able to look at that distribution and say, okay, I'm getting something that is supposed to be super unlikely. Is my model just wrong? If I keep getting these unlikely events, does that mean that my initial model was incorrect and that I need to revise it? This is like a really big application of the ideas of binomial distributions. Okay, so let me check that there's nothing else for me to say in this video. Nope. All right. So moving on, we are going to take a look at something called Pascal's triangle.